Hello, sir. You can start now. You are live.
Okay, thanks a lot. I think, all right. So, can you hear me? Backend, backend team, can you hear me?
Yes, sir. We can hear you clearly.
Okay, thanks a lot. Great. So, yes, so finally we have been able to start this uh, live interacting session. People have been waiting, so I'm really grateful that you have been waiting patiently for this. So it's a great pleasure to welcome you. This is our second live interaction session, and there will be one more towards the end of the course, 3 weeks from now. So please feel free to ask your questions in the chat box. There is the chat box where you can put in your questions. I will try to answer them as to the best of my abilities. Meaning this course has been going reasonably okay so far. There are a few questions and so comments. I should perhaps tell you that there is a mailing list which is called the discussion forum. So if you go to the main web page of the course on the NPTEL website, you will see Q and A. There is a link called Q and A, which is, if you click on that, you will be taken to Google Groups. Uh, there you have to go to the course Google group, which is the a basic course in number theory, NOC 25 MA 102. And then there are two uh, discussion fora, or there are two mailing lists to which you should be subscribed to. And the first one is about announcements, and the second one is what is called discussion forum. I think announcement, everybody is by default subscribed, but to the discussion forum, one has to go and join. So please join the discussion forum so that if you have any question, you can ask those questions there, and also the answers which are given to other questions, you also get to see that. So that is what we should try to do. There are some questions which are asked. So, meaning Google form was circulated and it was requested that if you had any question, then you should put in the question there. But there are very few questions which are asked. So I will discuss those questions. Some of those questions will require a detailed answer. So I will actually give those detailed answers, but I will also wait for other people to join. Meaning at least the person who has asked the question should be there so that, the person can see the answer to his or her question. Meanwhile, if there are other people who would want to, get any information or want to, have some question answered, please go ahead and ask me. I will keep talking until there is some question, and maybe 10 minutes after or so, I will go to that questions which are asked on the Google Doc. So this is, I should also tell you that this is called a basic course in number theory, which means that for number theory, it's a basic course. But it doesn't mean that, it is only something which will use very few prerequisites. That's not quite the thing. The main thing is that if you are beginning to learn number theory, then these are the things that you should learn. That is why we have discussed these things. But sometime, you will use some group theory, or later maybe some ring theory or field theory. So basic topics in algebra will also be used somewhere. But again, meaning I have tried to explain to the best extent possible what are the things that we are using and how they are being used. So sometimes, I like to say this in my classes also, that you should take some things as black boxes. There is a statement which we use, and the statement will require a proof perhaps. But if you are willing to accept the statement, and then from that statement, if you are willing to build number theory or whatever course you are doing, then that is something which is very useful. So after all, mathematics is infinite, knowledge is infinite, meaning you can keep on learning. But the thing is that there are a few things which you should accept. Even the set, basically what is a set, that is not a very clear thing, and it took up to last century to come up with a precise definition of a set. For many years, for many centuries, people were not clear what is a set, but still they kept doing research in number theory, kept doing research in mathematics. And it became clear only very recently how a set should be thought of. And then there are other things which came up. So there are various paradoxes which we see because the notion of a set was not very clear. So these things keep happening. What we should be willing to do is to have something which is understanding how to use the existing things to build the next thing. Right. So Kasina Dhuniji has asked this question. Please provide solution for week 7 assignment in detail, simply given as use formula, even suitable examples also not given in lecture sheets. All right, yeah, that's a valid point perhaps. So meaning the thing is that, so where did I say use the formula? Okay, so at some point I have said use, so there are two places where I have said use the formula. One is question 4, where we have asked for the number of square roots of 1 in a particular ring U, which UN have 16 square roots of 1. That is where I have said that use the above formula, but the formula is given in answer number 3, and the formula is very explicit. All one has to do is to take a number, write it as a product of prime factors, and then count what is the number of prime factors. So I think if there is a explanation required even to do this, then maybe one should really go to do a very very basic course in number theory. So perhaps you don't mean this. What you perhaps mean is question number 7 and 8, where I have said you use the quadratic residue formula. So I will, yeah. So this is where I have not explained things properly, but the thing is that we are looking at the primes. So let's look at question 7, right? So which is asking the quadratic residue symbol 21 sub p, 21 upon p, when is it equal to 1? This is the thing that we are trying to solve, correct? So when we are looking at 21, we know it is 3 into 7. And then the quadratic residue symbol, the Legendre symbol, will be 3 by p into 7 by p. Okay. So we want this 21 upon p to be equal to 1. So 3 by p upon into 7 by p has to be 1, which means that either both 3 by p and 7 by p is equal to 1, or both are equal to minus 1. Okay, so far I have not used any advanced mathematics. We have come to the point that what are the following primes which have the property that both 3 by p and 7 by p are either equal to 1 or both are equal to minus 1. This is the basic thing that we want to look for. So then we put the values. So for instance, if you put the value p equal to 41, let's look at 3 upon 41. So 3 upon 41, we see that one prime is 3, another prime is 41. 41 is congruent to 1 mod 4. So when you use the quadratic residue formula, so it will tell you that you can look at p by q and p by q by p, the two Legendre symbols, right? So 3 by 41 and 41 by 3. How are they related to each other? They are related to each other by saying that the product is equal to minus 1 to the power something. What power is it? It is 3 minus 1 upon 2 into 41 minus 1 upon 2. Now 41 is congruent to 1 mod 4. So 41 minus 1 upon 2. 41 minus 1 is 40 upon 2 is 20. So you have some number which is plus 1 or minus 1, and you are taking its 20th power. That will always be 1. Right? So it will tell you that the quadratic residue symbol 3 by 41 is equal to the quadratic residue symbol 41 by 3. Now you take 41 and go modulo 3. So we see that 41 is 39 plus 2, and therefore 41 is congruent to 2 modulo 3. Now 2 modulo 3 is a quadratic residue symbol, Legendre symbol, which we can easily compute. We know 2 is not a square. So 2 by 3 is minus 1. Therefore 3 by 41. So 2 by 3 is minus 1. So 41 by 3 is minus 1. Therefore 3 by 41 is minus 1. Okay. So coming back to our question, we were looking at the number p such that 3 by p and 7 by p have the same sign. Now we found that for 41, 3 upon 41 is equal to minus 1. We need to check whether 7 upon 41 is equal to minus 1. We use the residue symbol once again. 7 upon 41 will be equal to 41 upon 7 because 41 is congruent to 1 mod 4. And now 41 upon 7, 41 is 6 modulo 7. So we have to compute 6 by 7, the Legendre symbol. 6 by 7 is 6 a square modulo 7. 1 square is 1, 2 square is 4, and 3 square is 9, which is 2. We have found 3 squares, 1, 2, and 4. 7 modulo 7, there are 6 non-zero elements, out of which half will be squares. Those 3 we have already found. So 6 is not a square, therefore 6 upon 41 is minus 1. Sorry, 6 upon 7 is minus 1. So 41 upon 7 is minus 1. So 7 upon 41 is minus 1. All right, so 3 for if you put p equal to 41, 3 by p and 7 by p are equal. Therefore, their product is 1. Therefore, 21 upon p is 1 when p is 41. Okay, that is how one would solve these kind of problems. Meaning you would appreciate that at the moment I have not used any calculator. Indeed, for any of these things, we do not need to use calculators. We just need to observe when you can flip the residue symbol. Whenever the prime p or the prime q, whenever one of them is congruent to 1 mod 4, you can always get p by q equal to q by p. This is for odd primes, and for the prime 2 we very well know what the quadratic reciprocity law tells us and how to get the answer. I hope this answers Sham Sundar's question. If not, then please specify your question again and I will do this. Right, so your point was also that suitable examples are also not given in lecture sheets, but the thing is that the assignment problems are for that there are the examples are to be done in the problem sheets that we have. And I think in the problem sheets we have simply put problems which use the formulae. I have not put any problems which will require any further trick. There are of course some problems where you will need to use something more than what is already done in the lectures. I have deliberately, meaning this is an effort from my side which I am putting in, and I hope it's of some use, that we have put in problems which use only the given things in the lectures. Yeah, maybe you are right that I should do more examples. I will try to see what I can do. Yeah. Good. And thank you for your comment, Sham Sundarji. So now I'll come to Satindarji's question. Which of the following is isomorphic to U2024? I have the problem in this type of concept. Correct. So this is where we are using group theory. And so, whenever we look at two groups, we want to see which two groups are isomorphic to each other. The thing is that isomorphism of groups says that there is, what is the isomorphism? Isomorphism means that you have two groups G1 and G2, and there is a function from G1 to G2, which is a group homomorphism. And then of course we have that the map is 1 to 1 and on to. So the thing that this map is a homomorphism means that the two group structures are the same. If you are looking at elements of certain order in one group, the number of those elements should be the same for the other group as well. The number of elements of a given order, the number of subgroups of a given order, anything that you can do for groups, that should be the same for both the groups. This is what should be true. So when we are looking at, let me go back to this question, U2024. So I think it was, maybe it was in the previous assignment. Let me try to see assignment 6. Right. So it's in assignment 6, question 9. So correct. So what we should look for first of all is to write and understand the group U2024. So I think I have also given an answer here. So the answer also says that we have understood that the rings Z modulo 2024 is isomorphic to the rings which are obtained by taking the prime power factorization of 2024 and then taking the rings corresponding to each prime powers. So if you look at 2024, how do you decompose it? 2024 is 2 into 1012, which is 2 square into 506. And this is now 204, 2 cube into 253. And then I will go back to the solutions that I have to decompose 253, which is indeed 11 into 23. So we have decomposed 2024 in the prime powers, which is 2 cube into 11 into 23. So these are the three prime power factors that we obtained for 2024. Now Chinese remainder theorem will tell you that Z modulo 2024 is isomorphic to Z modulo 2 cube cross Z modulo 11 cross Z modulo 23. There are these three rings, Z mod 8, Z mod 11, Z mod 23. These three rings, if you take their product, you get the ring Z modulo 2024. And the invertible elements, Un is the set of invertible elements. So the invertible elements in 2024 is the same as the invertible element on the right hand side. Correct? So which is the set of invertible elements in each of them. So you have to look at the invertible elements in Z mod 8. Now we have seen that Z mod 8, there are 8 elements 0, 1, 2, 3, 4, 5, 6, 7. Out of those, which are the elements which are invertible modulo 8? Precisely those which do not contain 2 as a factor, because to be invertible modulo 8, the element should be co-prime to 8, which means that 2 should not be a factor. So you should look at all odd numbers. And since 8 has no odd factors, it is enough to look at all odd numbers. So 1, 3, 5 and 7. These are the 4 elements in Z mod 8 which are invertible in Z mod 8. Now, how does this group look like? I think I also wrote about this in one of the discussion forum questions, that 3 square is 9, which is 1 modulo 8. 5 square is 25, which is also 1 modulo 8. And 7 square is 49, which is also 1 mod 8. So this group of units modulo 8 has one trivial element, which is 1, and 3 elements, the remaining non-trivial elements, are all of order 2. So this group is isomorphic to Z by 2 cross Z by 2. It's the product of cyclic groups of order 2, two such groups. One also calls them C2. So we see that the Z mod 8Z is C2 cross C2. Okay, so Z mod 8Z units U8, that is C2 cross C2. So next we go to U11, the elements which are invertible modulo 11. But 11 we see is a prime number. So all the non-zero elements mod 11 are invertible. So that gives you a group of order 10. It is a cyclic group also. So you have C10. And for U23, you get UC22. So our group is now C2 cross C2, C10 and C22. But now there is one small group theory which comes here, which is that C10 is same as C2 cross C5. This is observed by looking at Z modulo 10Z. Again, the Chinese remainder theorem will tell you that Z by 10Z is Z mod 2Z cross Z mod 5Z. Similarly, C22 is isomorphic to C2 cross 11, C11. So we got 2 copies of C2 in U8, 1 copy of C2 in U10, U11, 1 copy of C2 in U23. So you have C2 cross C2 cross C2 cross C2, 4 copies. Then you have C10, C5, and finally you have C11. So 2, 2, 2, 2, 5, and 11. That should be the ultimate answer. Okay, so the option A is indeed 2, 2, 2, 2, 5, 11. Option B is where that last C11 is coupled with a C2 and you get C22. You see, whenever the numbers are co-prime, the product of cyclic groups is again cyclic. This is Chinese remainder theorem. Okay, so A, B, C will give you answer like that. But if you look at D, E, and F, in D, you have an element of order 4. There is a copy of C4 sitting there. C4 has an element of order 4, but U2024 has no element of order 4. Every element in the copies of C2s, you have 4 C2, 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 C2. But every element there is either the trivial element or its order is 2. So there is no element of order 4, there is no element of order 8, therefore E cannot be an answer, and certainly there is no element of order 40. Therefore, F is also not an answer. In fact, once you observe that there is no element of order 4, then D, E, F cannot be an answer because C8 and C40 also have elements of order 4. Simply by observing that there is no element of order 4 will tell you that the remaining three things cannot be isomorphic to U2024. So I hope this answers the question which was asked by Satinder ji. There is no other question which is given in the chat box, so maybe I can go to one of the questions which was asked in uh, the Google form that we had circulated. So there are, I think, 2, 3, 5, 2, 3, 4, 5, 6, 7, and 8. So there were 7 responses. 3 responses did not really give any question. One response said that keep the interaction session in the evening. I can understand that morning time may not be suitable for everyone. You may have your classes or some other thing, but unfortunately, my schedule is also a bit tight this semester, so I cannot have the interaction session in the evening. In fact, I can tell you that this is not the first time I am running the course. I have run it a few times earlier. And if I remember correctly, I had kept the interaction sessions in the afternoon for the first time I taught it. Then there was a request to put it in the morning. So next year, when I did it, I put it in the morning. And then there was a request to put it in the afternoon again. So I do understand that there will be students who will have some genuine reasons for not being able to present during these sessions, but then the recording is available for you, and I can understand that if you are not able to come and attend the session, you cannot ask your question. Only people who are here will be able to write their question in the chat boxes and hope to get their questions answered. So in that case, please give your questions in the Google form, because the Google form has some questions and I always try to make an effort to explain all the questions, to give answers to all the questions given in the Google form. Therefore, if you are, first of all, if you are able to attend the live interaction session, that is great. Whether you are able to attend or not, you should try to give question in the Google form. Okay, so that is one thing which will help you understand the course better. So this was Pushpa ji had suggested that I should keep it in the evening session, but unfortunately I will not be able to do it even for the next session. But please ask your mathematical questions here and we will be able to answer them to the best of our abilities. Right. So now there was a question from Priyam Priyadarshi, and he has asked something very interesting. So this is the student studying in ISI Kolkata doing statistics, and he has asked for some information where number theory will have intersection with probability theory. So the thing is that there is one part of number theory which is called probabilistic number theory. So for instance, the primes are the things which do not follow any law. Primes are randomly distributed. So to guess what we can do with primes, one thing we can do is that take a number n, and once you have the number n, you can ask how many primes are there up to the number n, and then let n go to infinity. This is the way we would try to get some estimate on the primes. The thing is that this involves a lot of probability theory techniques, and the very fact that primes are distributed randomly tells you that there is a probability theory which comes into picture, because then if the primes were distributed evenly, then probability theory would be of no use. Suppose you are asking how the even numbers are distributed. That's a very well known fact. If you are looking at numbers up to n, roughly n by 2 are even. So there is no need to even say anything about probability coming in picture for the study of even numbers, odd numbers, or numbers which follow a particular pattern. Primes don't follow that pattern. Therefore probabilistic number theory is something which is very useful. It's a branch of number theory. It's a very well recognized branch. There are books on this. There is a mathematician by name Immanuel Kowalski. Kowalski, the spelling is Kowalski. Kowalski. So Kowalski has a book on probabilistic number theory. I think if you search for Kowalski probabilistic number theory, this PDF file will be available online. You will be able to find it, and you can learn a lot more about probabilistic number theory, how to use your probability techniques in the study of number theory in this domain. So Priyam, I hope that this is an answer for your question. Let me see if there is any other question in the chat box. So, right, thank you Satinder ji for your comment. So Krishna Gopal Pradhan, question 10 in assignment 7. So let's go back to assignment 7 and question 10. I think assignment 7, the solutions are discussed recently, so I can discuss it. It's not that the assignment is yet to be submitted. I think the last date is over. Okay, so the question is, you are given some set of polynomials and you are asked what are the polynomials with the property that there is a root modulo every prime. So we are looking at some polynomials. So for instance, if you take the first polynomial, which is x square minus 2, x square minus 3, x square minus 6. So what are the possibilities? If you have a square root of 2 modulo p, then x square minus 2 will have a solution. For instance, if your p is 7, then 3 is a square root of 2, because when you take the square of 3, you get 9, which is 2 modulo 7. Okay, so 2 has a square root modulo 7. Therefore, x square minus 2 will have a root. If you put x equal to 3 in x square minus 2, modulo 7, you get 0. Correct? So, p equal to 7 is 1 prime for which your x square minus 2 has a 0. Therefore, the whole polynomial has a 0. Correct? Now look at x square minus 3. Suppose 2 is not a square. Suppose you are looking at the prime. Let's say you are looking at 5 will not do. Okay, so let's look at 5. But right, I think 5 should not. Let's look at 11. All right, so 2 is not a square root. 2 is not a square modulo 11. That is because modulo 8, 11 is 3 mod 8. So 2 is not a square modulo 11. This is the quadratic reciprocity law that we are using. Let's look at 3. What is the square of 5 modulo 11? 5 square is 25, and when you go modulo 11, 25 is 3 mod 11 because it is 22 plus 3. Therefore, 5 square is 3 modulo 11. 2 is not a square, but 3 is a square. Correct? So we have that the polynomial x square minus 2, x square minus 3, x square minus 6 has a root because x square minus 3 already has a root. Okay, so whenever 2 is a square, the whole polynomial has a root. Whenever 3 is a square, once again the whole polynomial has a root. So now the remaining case is when 2 is not a square and 3 is not a square. Let's look at this again. If 2 is a square or 3 is a square, I am putting an or between these two statements. If 2 is a square or 3 is a square, our equation, our polynomial has a root. And the negation is the only remaining case is when this doesn't happen and that doesn't happen. That means 2 is not a square and 3 is also not a square. So this is the example for p equal to 5. The squares modulo 5 are 1 and 4. 2 and 3 are not squares. That means the Legendre symbol 2 by p and 3 by p are both equal to minus 1 because 2 is not a square, 3 is not a square. When both of them are equal to minus 1, you take the product, you get the Legendre symbol for 6 upon p. Since these two are minus 1, 6 upon p has to be 1. Right? So 2 upon p is minus 1, 3 upon p is minus 1. Therefore, 6 upon p is 1. So your final factor in the polynomial, which was x square minus 6, that is now equal to 1. So therefore, either 2 is a square or 3 is a square or 6 is a square. These are the only possibilities. There cannot be any prime for which 2 is not square, 3 is not square and 6 is not square. There cannot be any such prime. Therefore, for every prime p, the polynomial given in the option A has a root. Similarly, you can look at polynomial given in C and polynomial given in F. Okay, so polynomial in C is 3, 5, 15. If 3 is not a square, 5 is not a square, 15 will have to be a square. If the polynomial in the last option F is, if 5 is not a square, 7 is not a square, 35 has to be a square. Okay, so A, C and F are understood. Now if you look at polynomial E, the third factor in polynomial E is x square minus 9. Now 9 is always a square. 9 is a square in the set of integers. Therefore, it is a square modulo any prime. Okay, 3 mod p is a solution for x square minus 9. So E is always going to have a root modulo a prime p, whatever the prime p is there. Now the options are B and D. You know, because I have said that there can be multiple correct answers, multiple correct options. So you have to make sure that B and D are not the correct answers. So for that you have to get a prime for which your B does not have a root, and that I have said that it has no root modulo 3. Similarly, you have to get a prime P for which D has no root. So you have to use the quadratic reciprocity law and produce a P such that 2 by P is minus 1, 5 by P is minus 1 and 8 by P is minus 1. But again, if you look at it very carefully, 8 by P is simply 2 by P because it is 2 times 4 upon P, which is 2 by P, 4 by P. 4 being a square is that Legendre symbol will be always equal to 1. So the Legendre symbol 8 by P is equal to 2 by P. So all you have to do is to find a prime P such that 2 is not a square mod P and 5 is not a square mod P. That is the prime equal to 3. Similarly for D, you have to find a prime such that 2 is not a square mod P, 7 is not a square mod P, that is the prime P equal to 11. Now you may ask, how would you know that B and D are not going to be the solutions? For that, meaning you will quickly observe that the 2 and 5 and then the product of 2 and 5 is not given in the last option. Similarly, for D, the product of 2 and 7 is not there in the last option. So it is perhaps possible. So one can try to find a prime P such that the corresponding numbers, which are 2 and 5 for B and 2 and 7 for D, have no square roots. And one very small things like, going up to prime P equal to 11, that already gives us the solution. So this is how, Krishna Gopalji, this is how one would solve the question 10 in assignment 7. Satinderji has asked, what is the application of quadratic residue of type fxy, which we solve by matrix transformation? Different types, we studied 2 types. I don't think I have understood this question. So fx comma y, quadratic residue of type fx comma y, it beats me. I don't understand the question. Satinderji, I request you to give some more details. And meanwhile, I'll go and see where about to discuss the problem. So Suraj has asked how to do research in number theory, which is related to distribution of prime numbers, and what are the most useful tools used in research. So distribution of prime numbers, I said just now that prime numbers are randomly distributed, and therefore the probabilistic theory is one thing which is used to study the distribution of prime numbers. So that is one thing. Second thing is a lot of analysis is used. So if you remember the prime number theorem, which tells about the estimate on how the prime numbers behave, how the function f behaves as n goes to infinity. F of n is the number of primes up to n. Then we have already used some analysis in studying that. So, the real analysis, complex analysis, this is used a lot in studying prime numbers. Also, some Fourier analysis is used. There is a lot of these things. In fact, the study of primes comes under the branch of number theory, which is called analytic number theory. So number theory has several branches. I mentioned probabilistic number theory, which uses probability to study number theory. Analytic number theory uses analysis to study number theory. Algebraic number theory uses algebra to study number theory. But somehow primes are not very well behaved with respect to algebra. The product of primes is not a prime. Sum of 2 primes is almost never a prime. Meaning, if you take one of the primes to be 2 and another odd prime, then there may be some chance of getting the sum to be a prime. But if you take 2 odd primes and take the sum, you will get an even number, which is never a prime. Meaning the only even number which is a prime, then it is equal to 2. So algebra and primes don't go very well together with each other. Analysis goes very well. Probability goes very well. So all these tools, analysis, probability, they are used a lot in studying the distribution of primes, and already, meaning not just in India but abroad as well as in India, there are many good mathematicians who are working on this. So I may also tell you about something which I recently learned. So there is this Goldbach conjecture, which we all know, which says that every even number bigger than 2 is a sum of 2 primes. But there is also another version of this which says that every odd number bigger than 5 is a sum of 3 primes. And it is believed that this problem is now solved. So there is recently somebody has announced a result saying that he has a proof for this. So I should tell you that what happens is that in all these kind of studies, it is typically easy to prove when your numbers are very big. So there is typically some capital N such that after capital N, every odd number is a sum of 3 primes. That is something which can be proved. But this number capital N is usually very large. So even if we want to use computers and check all odd numbers up to that capital N, because beyond capital N we know we have the result. There is something called circle method, which is developed by Ramanujan. It's a method in analytic number theory. So using that and some good estimates, one can prove that beyond n, every odd number is the sum of three primes. But the n that people had obtained was very big. So then mathematicians have been working very hard in bringing this n down. So there is a mathematician, I don't remember the name, but I think it came on Quora. So if you go to this Quora, which stands for QUORA, the question forum, that is where you will see that the proof for this result is set to have been announced. It is right now submitted, and the author is also there on Quora. So the author has promised then very soon he will come up with a version which he will put on archive. So we all look forward to this, and that would be a good point to see what tools are used in studying the distribution of prime numbers. So this is, I hope it explains the question asked by Suraj. Meanwhile, I think Satinder ji had said, okay, so binary quadratic form. I think binary quadratic form, Satinder ji, is this is not a quadratic residue. This is the binary quadratic form. What is the application of this? So binary quadratic form is basically which is the sums of squares, and we will see what are the numbers which can be written as sums of squares. So for instance, there is this theorem by Lagrange which says that every natural number is the sum of at most 4 squares. Okay, and already the binary quadratic forms will be used. So I should tell you that the whole course that we are doing, this basic course in number theory, is developed so that there are a few themes. There is the theme of prime numbers to begin with. Then there are congruences where we use prime numbers. After congruences, we came to quadratic reciprocity law where we use the congruences. After the quadratic reciprocity law, we have the binary quadratic forms. And the binary quadratic forms used our quadratic reciprocity law. Finally, we will be learning continued fractions, where we will study how to solve equations which are called Pell's equation, which were studied by Indian mathematicians much before Pell, which is also mentioned in the course. But those are the things that we will see. So all these things are going to be used in the further parts. Therefore, the applications of the binary quadratic forms or the discriminant of the binary quadratic form will be seen in the part of the course which is going to come next. So I hope that explains Satinder ji's question. I have maybe about 5-10 minutes, so I will take the last question asked in the Google form. And there are two parts of the question. Part 1 says that, can you please explain that lattices portion in the proof of quadratic reciprocity law? Second part says, to find the Legendre symbol 2020 upon 31, then we have changed 5 upon 31 to 31 upon 5. But for 101 upon 31, we don't change. Why, sir? Right. So I will come to the second question. There are two parts in Umaji's question. I come to the second part. The second part says there are two things that we have. The two Legendre symbols, 5 upon 31 and 101 upon 31. Now 5 upon 31, we see that the two primes 5 and 31, out of them, the numerator 5 is 1 modulo 4. Therefore, the Legendre symbol 5 upon 31 is equal to the Legendre symbol 31 upon 5. This is by the quadratic reciprocity law, which says that 5 upon 31 into 31 upon 5 is equal to minus 1 to the power 5 minus 1 by 2, 31 minus 1 by 2. 31 minus 1 by 2 is 30 by 2, which is 15. But 5 minus 1 by 2 is 4 by 2, which is 2. So you are raising the plus 1 or minus 1 to the square, which will always give you 1. which means that 5 upon 31 and 31 upon 5, the product is 1. Therefore, they are equal. Either they are both 1 or they are both minus 1. Okay. So this explains why 5 upon 31 and 31 upon 5 can be interchanged. However, for 101 upon 31, both the primes are, 101 upon 31 is also 1 mod 4. So indeed, one should do that. But 101 upon 31, I think the question is there that we need to make the problem even simpler. And when you have 101 upon 31, instead of working with 101 upon 31, we go modulo 31. 101 is still a big number, modulo 31. So we go modulo 31. 31 into 3 is 93. And 101 is 8 modulo 31. Correct? So the number 101 upon 31, that can also be changed. But it will not give us anything interesting because it will ask whether 31 is a square modulo 101, which is a more difficult question to understand. Therefore, we make it simple by looking at 101 upon 31 equal to 8 upon 31. 101 is congruent to 8 modulo 31. So this is 8 upon 31, which is again 2 upon 31. And now we know that 31 is congruent to 7 modulo 8. So 2 has to be a square. Therefore, we immediately get the answer that 101 upon 31 is equal to 1. We don't change because by changing, we would have made it more difficult. Okay, so this explains this, at least, meaning all the questions which are asked in the Google Forms are discussed to some extent. And I will now see whether there are any questions coming up in the chat box. And, meaning nobody has asked me for exam format. I am a bit surprised because typically everyone would want to know what is the format of the examination. But since no one has asked me, maybe I should not spill the beans. So I don't know whether I should discuss that or whether I should keep it for the last session. There is one more session 3 weeks down the lane where we will be able to discuss the remaining things related to this course. So maybe the exam pattern can also be discussed in that. Coming back to Satinderji's question, the discriminant of a binary quadratic form is something which is very useful. What one could do is this discriminant is, if you look at it very carefully. Right. So I was asking about binary quadratic form and its reduction from application. Okay. So how does the reduction help? So reduction helps because when you are reducing, you are applying some matrix transformations which are invertible. That means you can go from one form to another and also from the another form to the first form. So the values represented by one form is the same as the values represented by the other form, because the way you are going from one to another is simply by applying invertible matrices in integers, right? So if you have f of ab equal to alpha and you have a form g which is equivalent to f, you will be able to get a prime b prime such that g a prime b prime is alpha. Okay, so whenever you have two forms which are equivalent, then the values sets are the same. And if you want to compute the value set of a given form, it is very useful to reduce it to a simple looking form where we can compute the value set very easily and then go back. I'll give you an example. So suppose we have a form which looks like, I should just be careful that I should not talk about forms which are yet to be discussed in the assignment. Yeah, I think, meaning I cannot give any more answers because there is assignment 8 and what I talk about will perhaps have some bearing. So Satinderji, I am very sorry, but if you could come for the next session, then I'll be very happy to talk about how to use reduction. I cannot give an example today because the example may have some bearing. on the assignment 8. So I'm very sorry for that. I think it's now 11:24. We started a bit late, but we have been discussing for about 50 minutes now. A few questions have been discussed. If there are any further questions, I will be very happy to take them. But if there are none, then maybe we should wind up now because just 5 minutes are remaining. So let us see if there was, let me go back to the Google Docs sheet once again. Right, so Umaji had also asked about the lattices portion. So the lattices portion is indeed a bit difficult. But once again, what I suggest is that, you write it down. You take a prime P and you try to find out whether, the P by Q and Q by P are understood by looking at the lattices. Indeed, that's the most difficult part. And in the lattices, if one understands the lattices portion, one understands this quadratic reciprocity law proof completely. So meaning if I don't have anything to display and so on, then it would be very difficult to explain this part, which I cannot do now. But I am sure you please spend some time on this yourself, Umaji, if you are listening, and then I am sure you will be able to get it. The next class, programming mix, programming G has asked when is the next class. So I think the next class is 3 weeks down the lane. There will be an announcement. There is an email will be sent for the live interaction session number 3 for our course. So 3 weeks now from now, I think it's sometime in October, maybe the 6th of October or 13th of October. One of these two, maybe 4 weeks. So 6th or 13th, that is when we will have our next session. And that is when we will also be able to discuss the pattern for the examination. All right, so I get it back to the backend team. We are done from here. Thank you very much for joining, and thanks a lot to my backend team.
Done, sir? Hello?
Yes, we are done.
Done? Can I close, sir?
Yes, please.
Okay.